So, as I was saying, parameterized polymorphism is the last thing that we're going to look at as far as the four pillars go. We'd already looked at other forms of polymorphism, subtype polymorphism, the operator overloading, function overloading. But what parameterized polymorphism does is it allows you to create one class, one method, or one variable that can have different types at different points in the program. For example, you can create a list of integers, and then you are assured that you can only ever add integers to that list. Any attempt to add something that's not an integer is going to result in a compiler error like this. Or you can have a set of strings, right? You don't need a list implementation for integers and a string and a set implementation for doubles, right? You can parameterize it so that you only have one implementation, and that implementation works for any current and future classes, right? Here I've got a set of strings, a set of doubles as well, right? So what I want to do is I want to show a little bit more on parameterized polymorphism and how you can design and take advantage of it by doing a very simple task here. We're going to find the maximum, right? And we're going to do this iteratively. We're going to design a getMax function, okay? So my first attempt here is going to be a public static int getMax function, max. And we're going to take, say, a list of integers. And I'll call it list. Right? And we'll go ahead and we'll assume that the first one is the maximum. So int max is equal to list.get the first one. And then I'll go into a for loop. For I equals 0, I is less than list.size, I plus plus. We'll compare the current max that we've found so far with the ith element in the list. So list.get I. Right? And if that's larger than the max, then we'll update our max to the ith element, and we'll return max. Okay. And you might have done something like this, very similar in last semester, where you made this a little bit more general now. This is only good for lists of integers. But what I want to do is I want to make this a little bit more general, right? This only has one use. If I wanted also to find the maximum among a set of doubles, what would I have to do? I would have to copy, paste, and change this to a double, get the maximum among a set of doubles, right? And then I no longer get the first one anymore. What do to do this really quick and dirty, old school way of getting an iterator and then getting a next. That gets the first one. And since this is a set, there's no sense of what the first one is, second one is, third one is. So how do I iterate over a set? A for each loop, right? An enhanced for loop. So for element double x in the collection list, and I shouldn't call it list anymore, should I? I should call it set. Change, 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 change. And I can no longer get the ith element. Instead, I will compare the maximum to x. And if that's larger, then I will go ahead and put in x there. Okay. What are you complaining about? Oh, and also I need to change this into a double. Okay. But otherwise, it's the exact same algorithm, right? All I did was change a list to a set and integers to a double. Okay. So I don't want to do this ad hoc. I'd have to copy, paste, copy, paste, copy, paste for every single combination here. What I want to do is I want to make this more general. So let's start with the list and the set. What's more general than a list and a set? A collection. All right. So let's change that one to a collection. In fact, let's get rid of this one entirely. Okay. What's more general than a double and an integer? Oh, okay. There is a number in Java. In fact, it follows this inheritance hierarchy. You've got floats, doubles, and integers, as well as longs and shorts. They're all numbers. So what I'm going to do is I'm going to generally apply this to a collection of numbers. Now it's no longer, I'll rename it. It's no longer a set. There we go. And what are you complaining about? Oh, yeah. So it's no longer a double that gets returned, the first element, but a number. Okay. I don't iterate over a bunch of doubles, now I iterate over a bunch of numbers. And if max is less than, now here I can't use the inequality symbol anymore. I can't say, is this class, which is a number, comparable to this class over here, which is also a number? Which one is larger? What I need to do is I need to convert those to actual numbers that I can compare. Right? And the way that I'm going to do that is I know that this is a number. Everything coming out of this collection is a number. And if I look at the number interface on Java docs, or if I just use my IDE and use dot, I've got a lot of things that I can choose from here. One of those things is the double value. I can pull that double value out. A float will have a double value. It'll just be more precise. An integer will have a double value. 10 becomes 10.0, right? A double, of course, will have a double value itself. 3.14159 is 3.14159. And I can do that with both of these things, right? And if the maximum's double value is less than x's double value, then I can update max, and I'll return a number now. Right? Now let's take a look at how I can use this. So double max of, what's the first one? Sorry, a set of strings. Oh, it's not a set of strings. Numbers 2. There we go. Get max of numbers 2. Now this isn't going to work because it returns what? A number. So I have to make the return value here match number max. System.out.println max. But you can see that, system, there we go. And what are you still complaining about? Number is not applicable to set double. Okay, yeah, I know what it's complaining about here. That I can no longer do something like this. This has to be a set of, I guess I'm using numbers over here, number, there. The problem with this is that now, whereas before I couldn't add an integer, now I can. Right? Or vice versa, if I did it with numbers and I tried to add a double, it wouldn't have let me before, but now it will if I change this to number. Right? And this is not what I want. 3.54. Okay, good enough. Now let's go ahead and run this and see that numbers 2, the maximum value here is 30.3. And so that should run and give me 30.3. Good. What if I changed it so that it's the first numbers instead? Numbers, the first one. Now remember, this is a collection of both integers and doubles. I think that what was the maximum was 30 among this? Yeah, right here, this 30 right here. I don't want to have to do that. I don't want to be too general, right? I don't want all my lists to be numbers. I want some of my lists to be integers. I want some of my lists to be doubles. So what I did was I went a little bit too far, right? I tried to make this too generic. What I want to do is I want to use now here's where the parameterization comes in, the custom parameterization. What I want to do is I want to make this into any type, right? Before it was a collection of doubles or a set of doubles or a list of integers. Now it's a collection of numbers. I want it to be a collection of something, right? Now there's still a problem here. We'll fix that in a moment. But what is that a list of? Or what is that a collection of, excuse me? T, right? What is T? T is a variable. It's a type variable. Now the way to actually get this to work and compile is that you have to parameterize it. This Langle-Wrangle right here is saying that this is a polymorphic method. I'm going to parameterize it on some type, and I'm going to give that type a name. This is nothing special. You could call this type, or you could call it foo, all right, or just f. Usually, though, you use single capital letters to do this stuff. It's like a variable name, right? Whereas with a variable like int x is equal to 4, later on I can go x is equal to 5. I can vary its value. Well, I can also vary its type. Right? What value is x there? This is not real code because it doesn't belong to a function, but what value is x right there? It can be any type. Right? It could be an integer in one part of the code. It could be a double in another part of the code. That's what the polymorph is about. Polymorphism is about many forms, having code that can be applied to multiple different forms. Yeah. Well, I mean, it's not even inside. It's not even inside a method. It will be in a second here. In fact, let's go ahead and do this now. What have I done? I've said that I've parameterized this method so that its return type is what now? Its return type is variable. It depends on what collection you give it. If you give me a collection of integers, t magically becomes integer, and my return type becomes an integer. If you give me a collection of doubles, then the return type becomes a double, right? So I don't have to have multiple solutions. I just have to have one generic solution here. Now I do need to go through and make changes. For example, well, what type is max now? It's of type t, right? T max is equal to the first one. Then if I iterate over that collection, they aren't numbers anymore. They're not doubles. They're not integers. They're of type t, right, in the collection C. The big problem here, though, comes in with how do I compare the two values? Max is less than x. How do I do that if max is less than x? Now that's not Java code there. We're gonna have to figure that out. So what have we done up to this point? We started very low level. A specific kind of collection for a specific kind of type, a set of integers or a list of doubles. We made that more general by taking any type of collection. Right? We made it more general by making it into a number. And then we made it super general by making it any type of variable at all. Right? T. And that, T can be any type. It can be an object. It can be a string. It can be whatever you want. The consequence of going so abstract is that what can you say about T? What can here, I pulled out the first one. What can I say about max? What is max? What is its type? Is it an integer? No, not necessarily. Is it a double? No, not necessarily. The only thing that I can say about max is that it's an object. Max dot. You see all of these functions that are defined in the object class way at the top of all the abstraction. Everything in Java is a class or belongs to a class. Everything in Java starts at the base class called object. Right? It'd be like this if I created just a generic object O, right? And a new object. I think you could do this. Pretty sure that you can do this. Yeah. So what can you do with it? Not much. You can convert it to a string because everything has a toString method. You can compute its hash code because everything has a hash code. It's Java virtual machine memory address, right? But that's about all that you can do. So as a consequence, I've gone too far. I've overstepped my bounds, literally overstepped the bounds, and I don't have enough information to say this object and this object, which one is larger, right? So what I need to do is I need to put a bound on it. I'll say that it extends number. Right? Now the idea here is that T is some type that is a subtype of number. It could be double because double is a number. It could be an integer because integer is a number. It could be a number, right? Just a generic number. But I've given it a bound. Now I have a minimum amount. Oops, I don't want that. Now I have a minimum amount of guarantee here that anything in this collection is a number, and therefore I can use what I was using before, x dot double value. If that is greater than max's dot double value, then I'll go ahead and update it. And you see that that's actually resolved my problem down here. I'm going to go ahead and restore these to integer and double, respectively. Double. And you'll see here that it's complaining about me adding an integer to a list to a set of doubles. It's also complaining about me adding a double to a list of integers, but it's no longer complaining about getting the maximum anymore. Let's see, numbers was an integer, right? Yeah, integer. And so I can get the maximum, or I can go with a double max d. There we go. Get numbers on 2, and then max d. And I can have the same solution for any type of collection on any type of numbers. And this should work, I think it was 30 and 30.3, right? Still not good enough, right? What I did is I started very low level, and I made it more abstract, more abstract, more abstract, until I went too far, and it was too abstract, and it's all just generic objects. So I brought it back down and said that, okay, well, everything is a double, or everything is a number, right? But that's not the only thing that you can take a max of, is it? What else can you take a maximum of? A what? What else can you take a maximum of? Strings, because strings are comparable, right? Which one is the maximum among Alice, Bob, and Rizzo? Rizzo. Why? Because, yeah, last alphabetically. So lexicographic order, right? A to Z. This is the max over here. This is the min, right? All right. So can I use it? Can I say string max name is equal to get max of names, and then print that out? No. Why? It's not a number, right? So I'm going to make the, so I made it really specific, more general, too general, brought it back down a little bit. I need to make it a little bit more general now, right? So I'm finding that sweet spot, right, of very concrete, low down in the hierarchy, in the inheritance hierarchy. Bring it on up, too far. All right, bring it on down, too much. So I'm trying to find that nice sweet spot, that Goldilocks zone, right, where it will work for whatever I want, but I still need a minimum amount of information in order to compare two things together. What about strings? String A and string B, how do I compare them? What? Say again? Compare function. And what was that compare function called? Compare to, right? That's actually defined in an interface called comparable, right? So if instead of extending number here, I extend this interface has that compare to method, x dot compare to, right? Just like strings, because strings are comparable, numbers are comparable, so you can compare them. All the built-in types are going to be comparable. Compare to max, and if this is less than 0, then x comes first, or so I guess I want greater than 0. Then that means that x comes after max, which means that it's larger than max, and so I would update my max here. And now it's happy with all three of those values. Let's run it and see that we should get the 30s before and then Rizzo. Right? Cool. Right? But now I want this to apply to any type. Here I've got a list of bank accounts. Can I get the bank account with the most money in it, the maximum amount of money? Let's find out. Bank account B is equal to get max of, what were my accounts? There we go. And system.out.println B. There we go. Is that going to allow me to do it? No. My design, I started way down low, went up, and got the right sweet spot where anything that's comparable will work. But bank accounts are not comparable. Right? They implement an interface called owned, but let me go ahead and put in another interface here, comparable. Darn it. I think, is it comma? Yes, there we go. But am I going to be, yes, commas. Why you can use ands in the actual parameterization. I think you could use or here too. No. Okay, fine. It's commas. Now, what is it comparable to? A bank account is comparable to anything? Can I compare a bank account to a string? A bank account to a number? Well, kind of the balance, yeah. But a bank account to an orange, a bank account to an apple. Now, what do I want to do? I want to compare apples to apples, oranges to oranges, bank accounts to bank accounts. All right. There. Now, this interface requires one method and one method only, as all interfaces should. Interfaces should be small. That's part of the solid principles that we'll talk about here in the end. Public, int, compare to, and we'll take another bank account, that. Right? Now I need to compare this bank account's balance to that bank account's balance. Here's a trick. Return, let's see, if it's larger, I want it to be that dot balance minus this dot balance. There, nice neat trick. Is that going to work? Well, first of all, the compiler's yelling at you for some reason. Why? Well, that is perfectly fine. This is a double. This is a double. We require an integer. Should you be doing tricks like this, the difference trick? No, because 0.25 minus 0.5, so 25 cents and 50 cents, the difference is, well, a quarter. But when it gets truncated, it's 0. So a bank account with 50 cents and a bank account with 25 cents, they have the same amount. Effectively, they have the same amount, nothing. But that's not what we want here, right? That's a round off error to a bank, right? All right. So if this dot balance is less than that dot balance, then we will return something negative, right? This comes before that, so something negative. Else if this dot balance is greater than that dot balance, and I could use getters here, but it doesn't matter. It's private. Well, it's actually protected, so the class can see it anyway, no matter what. I'll return something positive, else return 0. Right? Don't stay away from the difference trick. Even if you've got integers, stay away from the difference trick because of overflow and underflow. Okay. Now let's go ahead and run this. Now it's perfectly happy over here. Why? Because it conforms to this. It's bank accounts, which extend the comparable to bank accounts interface, right? Because it has that compare to method right there. And when I run this, I should be able to get that bank account with over $1,000 in it. Yeah, $1,233. And that was the largest one, right? Yeah. I just made a bunch of random bank accounts. So when you go to design your objects, you might think, okay, assets or portfolios, I guess is what you're doing. I can go ahead and implement the comparable interface. And if you only have one way of comparing, that's perfectly fine. But there's the comparable interface only allows you to compare in one manner, by balance. What if I wanted to do by account ID? Right? I would need another function to do that. What if I wanted to do by the owner, last name, first name? I would need another function to do that. Or, more accurately, I would need a comparator to do that. So it's not wrong to implement the comparable interface. It's just that it's kind of limiting. You only have one way of doing it. Right? This seems so important that maybe it's already done for me. And it is. B is equal to collections dot max. Nope. Max of my accounts. Right? And you're going to get the same thing. Yeah, same max. There's also a min. I don't know what's the smallest bank account that I have right here. These are not real bank accounts. $70. Right? I have more money than that. Not much more, but yeah. All right, yeah, then back again. What does that actually look like? It's way more complicated, right? So T extends object, and it has to extend comparable, and then we've got this mysterious question mark here, which is a super of T, et cetera, et cetera, et cetera. I wonder what all that crap is. All right. We'll talk about it here in 1 second. Yeah?
What happens when you have to deal with like a collection of polymorphic types?
Like, well, yeah, it has to be some type, so...
They could be changed, like they're, I guess...
Everything's at least an object.
Subclasses of like another type, so you have to like, they could endlessly switch the entire time.
That's perfectly fine as long as they have a minimum interface.
Okay.
So a checking account, yeah. A savings account, yeah. Or you can put them like right here. I do have a list of bank accounts. They're both bank accounts. I'm treating them as their most general type, and now I can iterate over it and find, it doesn't matter if it's a savings account or a checking account, I can still find the maximum because they all have the same interface as bank account. Right? Yeah. You can't do primitives at all. You have to use their wrapper classes. It's not like C++ and templates in C++ where you can use primitives in it. You have to use the wrapper classes. In fact, that's one of the only 2 use cases of wrapper classes. Over here in a bank account, I would never do something like this. Right? We're not going to take points off for it, but we would highly discourage that. Basically, you're doing boxing and unboxing, that every time you actually want to use it, your code is replaced with that dot double value, and it uses primitive types anyway. Anytime you put it into a collection, it boxes it up around the wrapper class so that it can be fit into a collection. Later on, when we look at implementing our own lists, then we'll see why that is. It is because of memory. It needs to know how big they are. Some things are 8 bytes, some things are 64 or 16 bytes. Some things are 32 bits, so 4 bytes or 8 bytes or 2 bytes or 1 byte, right? It's all over the map unless it's an object. An object is always 8 bytes, and that's why we do it that way. You can't parameterize. Say what? An object reference is always a byte, right? Yeah. Plus some overhead, maybe, I don't know. I don't program in the Java virtual machine, so I don't know. But anyway, that's what you would have to do. So what was that mysterious question mark? For this, I'm going to go to my old school, not PowerPoint slides here, but slides, basically. Let's take a look at these kind of like toy examples, I guess you could call it. So I've got a public static void foo. It takes a list of, this is where the question mark comes in. What is the question mark? It's an I don't know. Right? It takes a list of what? Anything. Right? All we know about the stuff, basically, the stuff in this list right here, is that they are objects. In fact, we haven't even given them a name. The difference between the question mark and the T before is that we've given them a name. Here, they're anonymous. We don't even have a name for them. We can change that by parameterizing it and giving it a name. Now its name is T. So that if I pull something out of that list, at least I can say what type it is. Right? Before, I just had to call it an object because that's all I knew. But I still don't have any information about what item is, other than it's an object. But at least it has a name now. Right? So super generic, that's as generic as you can get. This is generic, but at least it has a name. And now we can give it a bound. Right? T extends bank account means that you have a minimum guarantee here that everything in this list is a bank account. Therefore, everything in this list has a get balance method. So you can iterate over them. Right? Anything that you pull out of that is going to be a bank account. Anything that and consequently has this method called get balance. So you can at least sum them up now. That only works because of the named bound that says that everything in here is a bank account because it extends a bank account. A checking account is a bank account. A savings account is a bank account because of the inheritance. Here I've taken away the name. Why? Did you actually use T anywhere in this code, lines 4 through 8? No. So if we don't need a name, we can make it a little bit more generic by saying, I don't need the name. Right? And now everything in this list is still a bank account, but now I don't need to use the name, so I don't have to name it. But if you do need to name it, then you have to restore that T. For example, Buzz here takes a list of accounts and another account, and if that account balance is greater than 0, so it has some money in it, we'll go ahead and add it to our list of accounts, and also return it just for whatever reason. Otherwise, we'll return null to say this bank account is either $0 or it's negative, in which case we don't include it in our report or something like that. Right? But that was only possible because of the name. If you had not named this, I would not have the guarantee that I could put it back into the list. That this T, this T, this T, those all are the same T. They all have to be bank accounts or checking accounts or something, right? But without a named bound, then I don't have anything like that. If it's all just question marks, right? Then you can go even further, right? You can T extends bank account, and then you can say that the list is actually a super type of T, right? So these are lower bounds and upper bounds. Kind of what I was doing with my my demonstration. We made it very, very specific, more general, more general, more general, too general, then we brought it back down, right? This is establishing an upper bound, and this is establishing a lower bound, right? That anything in this list is a supertype of type T. So in other words, if I made it a list of type, I want to say, if I made it a list of type checking account, that I could also put in a bank account in there, and that would be okay, because I'm basically, think about the inheritance hierarchy, bringing it up, or this is establishing an upper bound, everything is a bank account. This is establishing a lower bound, that everything has to be at least of type T. So that if I had a subtype of a checking account, I would not be allowed to put that in there, right? Everything would have to be a checking account or up to bank account. So it's narrowing in on the hierarchy here. And if you want to learn more about this, again, don't try to do stuff like this for your assignments. Definitely understand what's going on and why it is. But if you want to learn more about it, learn more about PEX. That's producer extends consumer super principle. And it's just a design principle on establishing bounds. I need to make it general, more general, more general, more general, not too general, which establishes an upper bound. And I may want to make it more and more specific, but not too specific. That establishes the sweet spot. Anything between here in your inheritance hierarchy is okay for this thing, and it can operate on it. Right? And it's the PEX principle. Okay. Again, don't worry about doing the details of this stuff. It's actually quite difficult to design, but once you've got the design down, once you've got something that looks very nice, like say this, right? That's very nicely well defined. Then you've solved that problem for the rest of your life, and you don't have to go back to it, right? It's kind of like regular expressions. Okay, now I need a regular expression, so I'm going to have to go back and remind myself of all these things. Okay, now I've designed the regular expression. Now I can forget about it, right? It falls into that category of you need to be aware of it. You need to be able to look up how to do it and when you need to do it, and you need to be able to recognize when to apply it, right? But you don't need to remember how to do it exactly off the top of your head, right? Unless you're in a bad interview or something. All right. So that is the last pillar. Again, you essentially want to use parameterization to make as generic code as possible so that you can apply it to many types and not have to write 50 different get max functions. It saves you time from having multiple different implementations. You can also place bounds on it so that you can get that nice sweet spot of everything below this inheritance hierarchy, everything above this inheritance hierarchy, and it'll work. Right? So those are the 4 pillars. The solid principles are something that came around about 20 years after object-oriented programming, and it was more of an observation of these are the best practices that people have been using for the last 20 years. Martin and Feathers are given credit to this in the early 2000s. These were patterns that they saw emerge from object-oriented programming that we've basically already covered. It's just another way of looking at it, right? The solid principles are single responsibility principle, open-close principle, Liskov substitution principle, interface segregation principle, dependency inversion principle. Okay, so it's an acronym. Single responsibility is simply just encapsulation. You should separate out responsibilities. Classes should not be God classes. You shouldn't have a class that does everything, knows everything, sees everything. Person class should be responsible for person things. An address class should be responsible for address things, and you shouldn't mix them together. You can have a relationship between them through composition that a person has an address, and so it owns an address object, but that's where that's proper, right? This is putting the address in the person, or even worse, the person in the address. That doesn't make any sense. As far as your first phase went, we made a post on Piazza about this, warning people. You loaded up CSV files, you persisted them to XML and to JSON. How many responsibilities does that sound to you? At least 3, right? Maybe even 6, right? Because if you load up because of assets and people, right? So in my implementation, I had, I think, 8 classes do this. That's because I used inheritance all over the place. We were looking for at least 2 classes. If you did all the XML and all the JSON in one class and all the data loading in another class, that was perfectly fine. That's what we were looking for. But if you did all of those things in one big giant class, we took off. If you did that all in the main, we definitely took off. Right? So make sure that you're following that single responsibility principle, separating out concerns. Right? Large classes means more responsibility, means that it's less reusable. Right? The open-close principle is that every unit, that is every class or module, think about classes for class-based object-oriented programming, should be open for extension and closed for modification. Is this big enough? Okay, there we go. Sorry. And it's basically classical inheritance. You extend the behavior in subclasses, but you don't touch the superclasses. You need to make sure that you have a well thought out inheritance diagram, that you're putting common behavior where it should be rather than down here, specific behavior down here rather than up here, because not everything has an APR, right? And that belongs where it belongs. But you need to make sure that whatever inheritance hierarchy you establish, that it's well thought out, because it's really difficult to change it later on. Think about this diagram from before. This goes all the way back to Java 1 25 years ago. They put in some time and effort into the design of this thing, because what if 25 years later they decide, I don't want a set to be a list. Or what if 25 years ago they did say that a set was a list? It was just an unordered list, right? That would have led to a very, very different hierarchy here. And a mistake 25 years ago means that we would still be paying for it 25 years later, right? And fighting this inheritance instead of using it and extending it. So you need to make sure that you're open for extension. That is, that you can go ahead and override methods. You can add state in the subclasses as long as you don't muck with the superclasses, because if you start mucking with the superclasses, that breaks any code that relies on the behavior of the superclasses. So if you've got a superclass and a collection of subclasses, and then you come along with a new class and you change the behavior up here, that breaks all the existing superclasses or subclasses. Right? The Liskov substitution principle is just a restatement of the rectangle problem. If S is of subtype T, so S, T, the subclass, superclass, then objects of type T may be replaced with objects of type S without altering any of the desired properties of T. That just means that you can treat an ostrich like a bird, you can treat a robin like a bird, and nothing should break. If something does break, then it's a violation of this principle, as we saw with the rectangle problem. If you take a square and you put it into this shape rectangle square hierarchy, and you change it so that it becomes a rectangle and it's no longer a square, well, it's still a square as far as semantically, but the real meaning is that it's no longer a square, it's a rectangle. So so you can't go and substitute a subclass for the superclass because it's no longer a square, or however you want to look at that. Right? So that's a restatement of the rectangle problem. Or the rectangle problem is a violation of the Liskov substitution principle. Interface segregation principle is where if you are going to design an interface, it should be as small as possible. In fact, it should be 0 methods, or 1 method, or at most 2 methods. And that's because you don't want to lock your interfaces in to having a lot of responsibility. For example, some of these things, serializable, clonable, random access, those don't even have any methods. They're just giving the class properties. For example, array list is the only thing that has random access because there's an array under the hood and you can access it based on its index. There's not even any method associated with this interface. It's just that you can do this for efficiency if you want to. Right? You want to keep them as small as possible. Say that I had a click event handler. I've got this button called save, and on click, I do want to say save the file. But if I put in the interface, this interface click event handler, if I put in 2 methods, on click and on double click, that forces you to define what on double click does. What would you do? So here's the save button. Click saves the file. What does double click do? Save. Okay. Oh, okay. Then That's an option. You can go ahead and do that. But should you be forced to make that choice? No. Instead, it would be much better if they had like a click event handler and then separately a double click event handler. And then you can mix them in as you want. I do want to go ahead and do that. So I can go ahead and implement two interfaces. I don't want to do that. Or you want to do that, so you'll implement two interfaces. I don't want to do that, so I'm not forced to implement them both. I'll just bring in one interface instead. Interface segregation principle. Separate them out so that there's at most one thing. It's basically kind of like the single responsibility principle, but for interfaces. You should keep them as small as possible. Right? Finally, the dependency inversion principle. High-level classes should not depend on low-level modules or low-level classes. Both should depend on abstractions. And here's an example that I've been trying to develop a little bit more. Say that I've got three libraries in a phone app. Library A, Library B, and Library C. They all give latitude and longitude locations, right? You see this all the time in your Android, right? This app wants to determine your location. Do you want to give it permission or not, right? So there may be lots of ways of doing that. For example, you could have a library that did it via GPS. You could have there's a GPS hardware on your phone, right, natively. It could be that there's an Android implementation of it that not only uses the GPS, but maybe it seeks out other Android devices in the room and it takes a consensus vote or something like that, right? There might be another implementation, another library that instead uses cell phone towers. There's a cell phone tower in range, and there's another cell phone tower in range. I ask it its locations, which are absolutely precise, and then I triangulate that to get my location. Right? So three different libraries, all providing basically the same functionality, but slightly differently. The first one has a get latitude and a get longitude that both return a double. Right? The second one returns an Android location object from which I can get the latitude and the longitude. The third one has a get latitude and longitude, but they're in radians. So if I want to make all three of these compatible, I would have to, say, do something like this. If I'm using library A, I'll create a new location, and that GPS locator, I'll grab the latitude, grab the longitude, create a new location. If I'm using library B, then I will get the location, get the Android native location, and then I will pull out the latitude, pull out the longitude, and create my location object. If I'm using library C, then I will go ahead and pull out the latitude and longitude, and they're really long, and convert them radians to degrees, and then I'll return the location. Right? What if I wanted to add yet another library? Else if, right? What if I wanted to add another library? Else if, else if, else if, else if. Anytime I want to add a new low-level module, I'm going to have to put in an if-else if condition here. In your project, if you are finding yourself using a bunch of if-else ifs to determine your business logic, you're doing it wrong. Right? If you use a bunch of if-else ifs when you are parsing out the CSV file, that's perfectly fine. But after that, we should not see if this asset is a deposit account, if this asset is a private investment, if this asset is whatever. Apply these rules instead. That's a violation of the dependency inversion principle. Right? So what should you do instead? This is client code right here. It depends on low-level classes, the GPS locator, the Android native, the cell phone GPS. So we've got a dependency here. My locator is dependent on which one of these three things I plug in. Right? So there's a dependency, a direct dependency on these three. I'm going to invert that. Right? I don't like that they call it inversion because it's more of a sidestep. So what I'm going to do is I'm going to take those three dependencies and put it on its side, and here's my locator, and I'm going to put something in between so that I'm no longer depending on these things. I'm depending on this thing in between, and these things are depending on this thing in between. That's how I'm going to invert the dependency. I'll define an interface called locator that specifies one method because of interface segregation principle. And then I will implement three wrapper classes, a GPS locator, an Android locator, a cell phone locator, all that implement this interface up here. That's Now this is the interface. Now everything depends on that abstraction instead of one thing depending on another. You will see this in practice when we start doing database database programming. There's a dependency inversion there because the Java code that you write will not depend on the fact that you're going to use a MySQL database. The Java code that you write will depend on an abstraction. Then MySQL also depends on that abstraction, so that you can come in and you can throw out MySQL and use something else like SQL Server, right? And not have to change any of your code over here. If you come in and change one of these libraries or add a new library, right? Say that we've added this brand new library that has some sort of GPS magic that gets your location for free or whatever, right? So did I have to change any of my code over here? Nope. All I do is make a wrapper class that depends on the interface over here. So extensibility and using dependency inversion is going to make your code a lot more extensible. Okay. Solid principles. Again, don't memorize them. Just know. There are these things called the solid principles, and they help me with OOP, and maybe I'll look them up in a couple of years and remind myself what they all are, et cetera, et cetera. Right? But of course, if you get into the habit of writing OOP code, then a good OOP code to begin with, then they just become second nature to you. Okay. All right, that leaves us with a half hour before we get into databases next time. So that gives us enough time to do one of those nice extra topics. Right? So we've already gone through some extra topic. What was the other extra topic that we went through? HTML? Did we? HTTP, there we go, HTTP. I've also prepared a little bit on concurrency. Right? Now, this is mostly going to be demonstrations, not you need to use this for your projects or anything like that. But I do want to show you the basics of concurrency, especially in Java, right? But more generally here. Now, to do this, I'm going to want to get into CSE. So eventually, all right, we'll see if Scott Chafin over here observes what we're going to do and maybe comes over and yells at me or something. Because we're gonna steal all the nodes on CSE today, right? First of all, concurrency. What does it mean that you've got multiple processes or multiple things happening at the same time? Right? You're all concurrently listening to me, for example. But when we talk, right? If I talk and you talk concurrently at the same time, we're talking over each other. You can't hear, right? So there are lots of ways of looking at this. First of all, asynchronicity. Right? You observed this last semester when I showed you that busy application that if I hit a button and it's busy, it freezes up. Right? And then the asynchronous action where I hit the button and I'm able to do other things in the web page because it does it asynchronously. It doesn't block the remainder of a program. So for example, if I have code-wise, if I have task 1, task 2, asynchronous task 3, task 4, these are done in series. So task 2 only starts executing after task 1 is done because it's synchronous. Right? Now, if I've got an asynchronous task here, this is not Java code or anything like that, but if I've got an asynchronous task 3, what that does is it kicks off and says, go ahead and start executing task 3. I'm moving on and with my life and doing other things now. So task 4 gets executed. Basically, task 3 and 4 might be executed in parallel. All you know, though, is that they're executed asynchronously. It's non-deterministic. You don't know which one is going to, are they in order, right? Does task 3 get done before task 4? It all depends on what they are. Multithreading is slightly different in that you have multiple threads running independent of each other, maybe on one core, right? One piece of physical hardware. And it allows for schedules. So on one piece of hardware, only one thread can run at any one time. So thread 1 comes in, it runs, and then it goes to sleep. Context switches out. Thread 2 comes in, runs, and then now they switch turns or whatever. That's where scheduling comes in. They might have, with multiple threads, threads are basically within one process. One process can launch multiple threads. They might have shared memory, right? If there's data that all threads need, right? Then some problems come in later on when which we'll talk about. Then you've got full parallel computing, and that simply means that multiple processes or threads running on different cores, generally the same machine though, at the same time. So I don't think anybody in here has a machine made more than 10 years ago. So every single one of you, except for maybe your phones, I don't know. Do phones have multi-cores? 4? Okay. It's just a $50 Samsung phone. Still multiple cores on this? Wow. Okay. So there's not a machine made now anymore without multiple cores. I've got 4 cores on my Mac, but with multithreading? No. Thread ripper? No, it's hyperthread. Thank you. Hyperthreading. I can actually run 8 processes. Maybe some of you have duos, so 2 cores, quads, right? 4 cores. Maybe you have GPUs, which have hundreds or thousands of cores, right? But they're stripped down GPU cores, right? So same piece of hardware, multiple cores. Distributed computing is where you have multiple processes or threads across multiple different machines. So like a cluster over in the Holland Computing Center where you've got 50 or 100 machines or 100 different nodes all working together, right? You can farm out jobs to 100 different nodes, actually physically different hardware. The benefits of doing something like this is efficiency. If something takes 10 minutes on one core, well, how long would it take with 2 cores if it did it in parallel? Here's 10 minutes of time, right? Here's 10 minutes of time. If I did it in parallel, 5 minutes of time, roughly, right? You're not going to get that guarantee, right? If you had 4 cores, what's it going to be now? 2.5 minutes, right? Roughly. Right? If you had 8 cores, right? Now only 1 minute, right? You can see the power of this, that all you need to do is add some more cores and you cut down on your actual physical time. Now there's CPU time, which is going to be the same or even higher because you're paying for this, all right? You're paying for the the parallel processing, etc. It doesn't come for free though, right? There's context switching. So when one thread is running and it's done and the scheduler says your timestamp is done here, it kicks you out, and another thread comes in, that's not trivial, right? You need to context switch in. That means restoring the stack space. That means restoring memory, loading memory, and changing things around. You also have synchronization. If 2 threads are sharing the same data, you need to make sure that they're not stepping on each other's toes. If this comes in and changes it, and this thread is unaware of it and makes bad decisions because of it, you don't have synchronization. This is why immutable objects are awesome, because it's thread safe to begin with. Right? You have race conditions. Right? You've got 2 independent threads. Who gets there first? And does it matter? Right? You have starvation, where one thread is waiting for a resource, and another thread takes the resource. All right, I'm done with it, puts the resource down. As it's about to take that resource, that extra memory or something, another thread comes in and grabs it. All right, I'll wait. Another thread, okay, put it back. All right, I'll take it. No, another thread comes in, steals it. A thread could be starved to death and not actually do any computing. Not all problems are also parallelizable. In fact, that's some theory on whether or not NC is equal to P and a whole bunch of complexity theory stuff, right? So not all problems are parallelizable. You can't just take a problem and split it up. Right? There are some problems that are inherently sequential. You have to do it like this. You can't split it up and then do it in parallel. Right? So I want to give you a demonstration for the remaining 20 minutes here. So first of all, let's take a look at CSE. You can play along if you want on CSE. HTOP is this very nice utility that tells me what's running on CSE at any one time. Let's decrease the size here. And there we go. So right now, somebody in is running the 322 grader, it looks like. Looks like Ryan Patrick is running, somebody's running Java now in 322. Oh, hey. That's you. There you are. Oh, you're running HTOP too. You were running HTOP, I just saw you. So first of all, how many cores are there on CSE? well, there could, I don't know how many cores, maybe 32 cores, and it has hyperthreading, I don't know. But for all intents and purposes, 64. If I do htop on my machine, you can see that I've got 8 cores, but that's because of hyperthreading, so I really only have 4 physical cores, right? I'll go ahead and get rid of that. Okay, you can see that at any one time, like that core was being used 80%, but now it's down. That core is being used 63%, right? So let's go ahead and go into some demonstrations here. Let's see, do nothing. Right. And I'm going to run that in the background. Hi, I'm process 2468. Right. Okay, and it's going to say that every 3 or 5 seconds or something. It's running in the background just saying, hi, hi, hi. Let's go ahead and go with htop and see if we can find it. There I was. Where is it? There. User Seabird. There. I'll only look at mine, and where is it? Do nothing. There it is. How much CPU time is it taking? 0, because it's not really doing anything. So I'm not going to be able to see it up here because it doesn't take a lot of resources to say hi, right? But it is running continuously. I can use a utility called PS to list all the processes. And you see that there's the do nothing process that's running independently of my shell process here. I can send it an abort signal to kill it, and it's terminated. Right? If you look at PS or top again, you can see that it's gone. Right? Let's do lots of nothing. Right? Okay. Yeah, I'm only going to do 3. Right? So do lots of nothing. There. Now I've got three processes running at one time. There they are. They're each saying hi every 3 or 5 seconds. If I look at this, user cburk, right? There they all are. Right? It's running sleep in the background, but I've got do nothing. Three do nothings here. Right? I want to kill them all. I can't kill them all with just 1 command. I have to do it with 3 commands. There. I killed them all. Right? Yeah, there we go. All right. So that's launching a lot of processes. You can also do something called a fork bomb. So let me look at this code here. This is actually C code now. Fork bomb. All right, let's read what this is. Well, here, let me increase the size here a little bit. Let's read what this is going to do. All right. So we're going to come in here. We're going to get the process ID, and we're going to echo it like I did before. Hi, I'm process whatever, whatever. Then I'm going to go into a for loop here. And I've got it set to 4. I'm going to kick this down a notch for a second. And then we get our process ID. And if it's less than n, right, then we're going to fork. Forking is what I basically I launched a new process. Now, forking in C means that an exact copy of this program will then be cloned in memory, and it will be running exactly with the same variables and values as the point that when you forked it. Right? And then I say, I'm launching another process. So fork, 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 fork. What if one process forked 2 processes? What if those 2 processes forked 2 processes? What if those 4 processes forked 2 processes each, now 8, right? So this is called a fork bomb because you can, now if I did this outside of a for loop and just did it in a while true loop, right? Now I've got a true fork bomb that is going to fork, 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 and then we would definitely be getting a call from Scott Chafin. I think that you're limited to maybe like 64 processes or something. There's some limit there, so you're not going to kill the whole system, but you would definitely not be able to log back in until Scott takes care of it, right? Because you'd use up all of your quota, right? So let's go ahead and kick this down to just 2. There, and PS. Oops. Okay, it's done. I do make them go to die after 3 or 4 seconds here. So let me go ahead and do it in the background. And you can see that I've got actually 4 here. Why 4 if I did just 2? Let's diagram that. So the first one launches, so it goes into a loop, 0, 2, 1. And for each one of those loops, it launches another process. Sorry, on this one. Launches a process, launches a process. Well, this one inherits the, I don't want to call it inheritance, but it gets the 0 value, so it has another iteration of its loop in which it launches another one. 1, 2, 3, 4. How many processes do you count there? 1, 2, 3, 4. So what if I did 3 instead? You could diagram that out, and it would be run this in the background, run PS, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. There should be one more there, but I don't know why. The original died. 8, okay. And is that it? You're all done? Okay. I thought it was 9, but oh well. 4. How many? Predict how many there will be here. Should be 16. You can go ahead and count those up yourself, right? Because of the nested nature, but now it's nested with a separate program, right? And we'll let those die here. So you could do a fork bomb. I'm not going to do it because I am limited to, let's see, max number of processes, 1,024. So you can have at most 1,024 processes. I believe that that's the number on the CSE system, right? And, oh, I thought it was 15 minutes last night, but apparently he's kicked my CPU time down to 10 minutes. So maybe it's because of what I was doing last night. I was just testing this stuff. But you can check it out and see what your limit is. You can't have a process running more than 10 minutes. Otherwise, it'll be killed automatically. Right? So a thread is an entity. Those are all processes. A process is an executing program in memory. A thread is an entity within a process. And so you have one process that can launch multiple threads. Right? In Java, there are lots of ways of doing this. You can have a pure thread, which is a full thread implementation, and then you can launch that thread. You have something that's called callable, which is the reason that you have multiple different ways of doing this is because how do you want it to behave? Do you want to launch a thread and just let it independently compute and you don't need the result? If you need the result, then you would need to use a callable. Right? That'll return, it'll block and say, I'm not done computing yet. I'll let you know when I'm done computing. When I'm done computing, then I'll return the result, and then I'll wake you up for it. Otherwise, I'm going to block you, and you're going to go to sleep, right? So one thread can block another thread, meaning that it puts that thread to sleep and then wakes it up when it's done. Runnable is like a thread, but you don't need a result. Go ahead and run. I don't need a result there. Future is another way of doing it, which is the way that I'm going to show you here in a second. And it provides a future value, right? So I want to compute this number. I want to compute the number of primes between 1 and 1 million, right? And so I want to know, is this a prime or is this not a prime? I will put this into a thread, and that'll have some future value, true or false, or 5 billion or 6, right? It'll have some future value. It's allowed to run independently when it feels like it needs to run, right? There's an entire thread manager that manages all the scheduling and stuff like that. If I ever ask for it, it'll tell me, yes, I've computed the value, here you go. Or it'll say, no, I've not computed the value. Again, I'm blocking you, and I'll let you know when I'm done with it. Right? It's some future value that I can then ask for it at a later time. Here is a demonstration of that. And I'm in multithreading. I've got a lot of different ways of doing this. Here's a prime generator. I'm actually going to count the primes. Right? I want to know, don't worry about that stuff for now. Don't worry about that stuff either. Let's see, how many primes are there from 1 up to 1 million? Right. Does anybody know? A lot, okay. Well, we'll do it in serial first. I'm going to brute force it. I'm going to go, is 2 a prime? Yes. Is 3 a prime? Does the C of Eratosthenes? It says yes. All right, 4, is that a prime? No. 5, 6. It goes through every single one and brute forces it one by one by one. And I get an answer here. It shouldn't take that long. Only 0.2 seconds. 78,498. I don't know, do you believe me? Number of primes less than 1 Would I do 1 million or 100,000? Is that a million? All right. Hey, all right. I got it right. All right. How many primes are there from 1 million up to 10 million? So this is 10 times as big. The sieve of Eratosthenes is going to be exponential, so it's not going to be 10 times slower. It's actually going to be way slower than 10 times slower. It's running. There, 4 seconds. So 0.2 seconds up to 4 seconds. That's what? 20 times slower? Something like that. So 20 times slower times 4 seconds. If we go up to 10 million or 100 million, what's that going to be? 4 seconds times a factor of 20, that's 80 seconds. So this will execute in what? Minute and a half? Okay. That's a good estimate. We'll go ahead and say that that's true. I ran it last night and it was 1 minute. Yeah, about 1 minute. Okay. Now, what if instead of brute forcing it in serial, I'll brute force it, but using a callable? I forget why I called that. Okay, that's a copy paste. I was cracking passwords with it in the previous one. So all this is doing here. Let's go over here. Yeah, there it is. So what I'm doing is I'm creating a new thread pool. How many threads am I actually creating? 8 of them. So if I have 8 threads, and it took, say, a minute, say 80 seconds, and with one thread, with one process, and I parallelize that with 8 processes, what I'm doing is I'm starting, I split it up. If it's 1 million, I divide that into 8, and you take the first eighth, you take the second eighth, you take the third eighth, etc. And that's how it's working here. Again, don't worry about the details. About how long would it take? If in serial it took 20 seconds, how long should it take in parallel with 8 threads? Or it took 80 seconds, I think. It was our estimate. It should only take about 10 seconds, 10-ish, right? And by the way, while we're looking at this, that's my CPU. I'm running this locally. You can look at all my 8 cores, right? My actual CPU time here is, oh, it's done, it looks like. Yeah, it's done. So it only took 20 seconds, 29 seconds, 20 seconds plus the cost of doing business, right? And if I went up 10 times, what if I did 16 threads instead? Would you expect it to take now half as much time, so 15 seconds? It's going to take exactly the same amount of time. Why? How much physical hardware do I actually have? 8. So even if I have 16 threads, only 8 of them can be running at any one time. Right? So there's always some sweet spot there that you need to tune. There's no point in having 1 million threads when only 8 of them can run at a time. Right? And you can see that it's really cooking here. My fan kicked on. Right? And are you done? Yep, looks like it. So about the same time, 3 seconds fewer. Right? Now, here's what I promised. Let's steal all the cores here. So, what was it? Java. Dang it, what was it? Prime generator? There we go. Okay. I forget what this, I think this is only 8 cores. There we go, 6 seconds. Let's do that again. I'll do it in the background though so that we can take a look. There, I did steal all the cores. All 64 cores are going to me right now, but only for 6 seconds. Right. There. We can bump that up. Prime generator.java. Let's not go with, how many is that? There's 100 million. Let's go with 2 billion. And instead of 8 cores, let's go with 64. I don't know why I was stealing so many when it was only 60. Probably they were creating threads, or I don't know. Maybe it was because garbage collection does run in its own thread, but so many of them. Yeah. So I'm still stealing 64 cores there, and you can see all the tops are okay. Yeah, and now it's done. Oh wow, that was really quick too. Oh, it didn't print anything. Aw. Or it printed it, but then I got erased by htop. So let's run it again because it was really quick. 1, 2, 3. So this is how many there. 5 million, 5.7 million, 5.7 million primes from 0 to 2 billion, and I was able to compute that in 6 seconds. Of course, if I only did this with one core, how long would that take? But at least I wouldn't be stealing all the cores. I am. Okay. It might, oh, was it done already? No way. There's something else going on here. 1, 2, 3. Oh, wow, okay. It's just really, really fast on CSE, I guess. There's something else going on here, I'm sure. But you can see that I can steal all the 64 cores. You can do this with HCC. They limit you to the number of nodes you can grab as students, and then of course they sell nodes to other people to do distributed computing. So you can imagine that, and of course you can do this with AWS. You can buy nodes from Amazon, or you can buy nodes from Microsoft or whatever, and run massive parallel and distributed computing on those platforms. But you can see the advantage, right? That if you've got 2 cores, then that kind of cuts it in half. If you've got 64 cores, then 1/64th, right? And parallel processing and multi-threaded programming is what allows you to do something like that. But of course, you have to have a problem that lends itself to that. You have to be able to cut up a problem into, divide a problem into parts that can be independently computed. And not every problem is like that. But that's a quick demonstration on multi-threaded programming. You would want to take at least one course, maybe 2 or 3 courses on parallel programming to actually, fully appreciate the entire area. All right.